6 hours in the yard, and my allergies are really bad.
Yeah, mine have gone crazy the last 4 or 5 days.
I finished, my family finally finished that chicken coop.
Whoa!
Nice.
Hello? There we go. My mic wasn't working again.
What'd you do?
I helped build a grill
Nice.
and had a fire in my backyard, like a fire pit,
Yeah.
Yes, and that's about it. But my allergies have also been going mad. Like, I can barely breathe out of my nose. It's pretty bad.
I have gotten no allergies.
That's good.
Allergies.
Yeah.
Lucky.
Yeah. So, okay. Well, we got about 2.5 weeks to the test. Does anybody know what day of the week? The 14th?
The 14th, yeah.
What day of the week is it?
Tuesday. No, wait. That's wrong. 14.
Tuesday?
It's
Thursday.
Thursday, yeah.
Thursday. So we have 2 weeks from this Thursday. So yeah, 2.5 weeks. So, Savannah logged into AP Classroom and you found they were just sitting on your front page, correct? These questions?
I had to go to where you unlocked the free response questions and multiple choice questions, and then I went to optional practice, and it was a whole list of them.
And they had did they have a little green symbol by them? Like a little circle? Yeah. So that's new. Those ones are new as of the last week or two. And those ones I'm guessing those are the best practice for the test. So this one was Unit 5. Approximately how many questions were there, Savannah?
Just on the first 3 that I did, it was just the first, I said Unit 5, and it was just one question with a whole bunch of A, B, C and stuff. And then the whole bottom of the list, they combined units. So I'm thinking it's going to be more than one question.
Okay. So in terms this is one question. It's a long essay question. So I'd count this as one question. Was there 6 questions?
Just on the ones that I did, they were only one question units.
And you did 3 of them?
Yeah.
And then there was combination of units past that. So was there a few more questions, 3 more questions or only 1 more question?
I didn't check the other ones.
Okay. So we'll see. There's a handful of questions. You guys should, between now and the test, probably do them all. So we'll probably, we went all the way back. We've done the 2019, the 2018, and the 2017 practice tests or the test questions. So now we'll work on these. So I might have Savannah keep sending me them, if that's okay. Because, again, they don't show up on mine at all, which is very strange. So, yeah. Okay, so let's start. This one was from Unit 5. It says, decay of the radioisotope iodine-131 was studied in a laboratory. Iodine-131 is known to decay by beta emission. So we haven't covered this. Actually, this is exactly what I'm doing in my physical science class this week. We did it in chemistry a little bit when we talked about nuclear energy and a nuclear reaction. So we should just review alpha and beta decay. But first, this is an isotope. So iodine, does anybody have a periodic table, or could you guys look up what element?
I do.
Yeah, what element is iodine? What's it?
The 53rd.
53. So we can put iodine. The 53 is the number of protons, and it always goes in the lower left-hand corner. Sometimes books will refer to this as the Z number, but that's basically atomic number. Okay, and then
I remember a little bit of that.
What one?
I remember a little bit of that.
Yeah, and then what's the 131 called?
That's the mass, atomic mass.
Close. It's called the mass number. Now, if you look at iodine, remember on the periodic table it says its average atomic mass or relative atomic mass is 126.9. Okay, that's an average of all the isotopes. So this isotope specifically has a mass number of 131. So if you get say an isotope that has too many neutrons or too few neutrons, it's going to be unstable. So it turns out, and we don't, again, chemistry, unless you're a nuclear chemist, you don't talk much about neutrons, but Neutrons help stabilize the nucleus, okay? And if there's the wrong imbalance, or if they're imbalanced with the protons, then they will become unstable, which is, we call it radioactive, right? So this one's going to decay, meaning it's going to break down, okay? And it breaks down into two particles. It's going to break down into what's called a daughter isotope, and then a radioactive particle, so radiation. Okay, and it tells you that the radiation is known to decay by a beta, and the beta they wrote like this. Okay, a beta particle is essentially an electron. Okay, that's, if you guys want to think of it as an electron, it's basically an electron. It's what it is. It's a proton that's being converted to an electron. So this is weird. You shoot out basically this electron, and what happens is your protons increase by 1. But just think of it like a little algebra equation. You've got some unknown. I'll put the unknown in black. And you have to figure out those 3 things about it. So you just do some algebra. This one, the mass number up top is pretty straightforward. If you had 131 equals x plus 0, right? What's x have to be?
131.
It has to be 131. Okay. Then we do the same thing here. 53 plus 53. Oh, sorry, that's hard to read. Let me do it down here. 53 equals, we'll call it y, or we'll call it z this time because it's actually the z number, plus -1 or -1.
So 54.
Yeah, so 54. And then, now that you know this is 54, you can look up element 54 on your periodic table. So what's element 54?
Oh, okay.
Oh, that would be xenon.
Xenon.
Yeah, so it basically, iodine decays to xenon. It's weird. By decaying, it's actually going up by 1 proton. So beta emission, when it shoots off, so this little particle basically leaves high energy. It's probably like capable of penetrating into your skin. That little particle shoots out of the nucleus. So you have this big, giant iodine nucleus. It loses a little beta particle, and what's left, the daughter isotope, is called xenon 131. Okay? Does that make sense?
Yeah,
Yep.
it does.
Okay, and then we could do an alpha particle like this one, uranium 235. Uranium is element number 92. It's known to decay through an alpha particle. So an alpha particle, if you guys, here's the review for it. Do you guys remember what say element alpha particle is equivalent to? What element?
Is it?
Hydrogen.
Yeah.
Not hydrogen.
Oh, is it? Well, so let's see. It has
2 protons.
Oh, helium.
Helium.
Yeah, so this is a helium nucleus, basically. It has 2 protons and 2 neutrons. Okay, and so an alpha particle is a heavy. It's relatively heavy heavy radiation. Okay, but it's easily stopped because it's heavy. So I think, if I remember, and I got to review this, I believe alpha particles you can stop with like a piece of paper or a thin piece of metal. Beta particles, they take like more like concrete or cement, and then gamma particles, or maybe it's the other way. Maybe beta particles require like a lead sheet, a thick metal sheet, and then gamma radiation requires concrete walls. Gamma radiation is some of the most harmful.
Oh yeah.
So, but okay, anyways, this is an alpha particle. So what would uranium then decay to? So here you have 235 has to equal something plus 4. So what's that something?
231.
231. And then, hey, 92 has to equal something plus 2.
90.
90. Oops. And then once you know that that's 90, you just go back to, and that's thorium.
Weird.
So uranium 235, which is probably the most, that's what we built the atomic bombs out of. It naturally decays to thorium. Okay, but what we did with atomic bombs during World War II is basically we split uranium into 2 pieces, and this I'm just guessing, maybe we split it into like 170 and like 62, and 30, and I think we lost some neutrons, so 235, let's say 63, plus we lost some neutrons. So I think 62, element 62 is, where are we at? Like say SM, I don't even know the name of SM. I should have picked a different one. And then, yeah. And then,
Oh,
62.
Samarium. It's Samarium.
Samarium, and then 30, element 30 zinc. I don't know. I just made those up. But this is what happens in, say, an atomic bomb. This is called fission. So instead of ejecting a small like alpha or beta particle, what happened to the nucleus?
It's split.
It's split into two big pieces. And when you split something into two big pieces and then those stabilize, that releases a ton of energy. And these two neutrons can go and collide with uranium again, and that causes another uranium to split. And you get what's called a chain reaction.
Nuclear fission.
Yeah, that's called fission. When you break a nucleus, into two large pieces, that's fission. When you eject an alpha, beta, or gamma particle, then that's called radiation. And you guys remember a gamma particle? Gamma particle is like the little weird vertical fish-looking thing. What's the mass and charge of a gamma particle?
Is it really? Oh,
Yeah,
wait,
It's
how?
really so dangerous. It doesn't have mass, but a ton of energy.
yeah. It's just pure energy. Okay.
Whoa.
So there you go. Okay. So that's a gamma particle, and I don't think they're going to heavily emphasize that. So we've got this. Are you guys okay? This is called a nuclear equation.
Yep.
And we don't deal with them again because we always deal with electrons. You'll notice there's no electrons involved in here, right? There's no charges written.
Yeah.
So nuclear equation is just protons and neutrons, and then chemical equations, which are much more useful to us because they won't kill us because nuclear equations.
Okay, well, I wouldn't say that because
Okay, they can, but they're useful to us. Yeah, so chemists don't do nuclear stuff usually. Okay, moving
are
on.
you saying that all nuclear physicists are useless for it?
No, they're important. They're important.
Oh
They do a
wow.
lot more dangerous work than we do.
Yeah. Okay, write a balanced nuclear equation. We did that. Okay, what is the source of beta? What is the source of the beta particle emitted from the nucleus?
A neutron splitting into a
Yeah, so a
proton,
neutron, hey,
electron.
basically a neutron changes to a proton plus electron, and the electron leaves as a beta particle. So if you lose the new electron, then you're left with an extra proton, and that's why up above iodine changes to xenon, is basically you've changed a neutron to a proton.
Wait, I'm confused.
Okay, imagine I'm going to do a smaller particle, but here's a nucleus, positive, positive, positive. I'll put a negative, so a neutron and a neutron. Okay, so I have two blacks and one red, right?
Yeah.
Or sorry, three blacks and two reds. I don't know what I'm talking about. Okay, so 3 and 2. Well, what happens is I'm going to highlight this one. Let's say that turns into a black and a green. Okay, the green is an electron, right?
Yeah.
So overall, hey, do you guys see a proton and an electron? What's its overall charge?
Negative.
Proton and
Zero.
electron. Yeah, so a positive and a negative. What's its overall charge?
Zero.
Zero. And then, hey, what's this red neutron? What's its overall charge?
Zero.
So what's happening, if you want to think of it, Savannah, like this, a neutron is really a proton and electron mushed together.
Oh, okay, yeah.
Okay, because they cancel each other out. So a proton is really just a neutron, a neutron is really just a proton and electron mushed together. So what happens if you say shoot this electron off, then what's left right here?
Just the proton?
Just the proton. So this scooches over, and now I have 1, 2, 3, 4, and I'm only left with a single neutron, right?
Okay.
And so what that does, that went from, we started with 3 protons, which would be lithium, and now we have 4 protons, which would be beryllium.
Okay.
So beta decay, it's weird. Beta decay is actually a neutron that's shooting out its electron. It shoots an electron out. That electron's called a beta particle.
Okay.
Okay.
So
Okay.
basically, the neutrons are just an electron and proton duct taped together.
Correct. Correct.
Wait,
Which-
I have a
I
question.
hope
Yeah.
the bond is stronger than duct tape.
Nuclear duct tape.
Nuclear duct tape.
Okay.
Mr. Ford,
Yeah.
why doesn't a regular, like if a neutron, right, is just
Yeah.
an electron and a proton,
Yeah.
then why don't protons and electrons just fuse regularly?
Because electrons have a lot of energy and they're far from the nucleus.
Okay, then how do
And,
neutrons
and
come about?
they have a lot of momentum. Just like, hey, why doesn't the Earth crash into the sun?
Because we're rotating around it.
Because we're moving really fast, right? And we're basically we're at equilibrium. Our momentum and our centripetal force is pulling us outward, right? And the gravitational pull of the sun and the Earth is pulling us inward, and we've reached equilibrium, right?
Yep.
So the electrons orbiting in these orbitals have basically found an equilibrium state where they're happy staying away from the nucleus.
Okay.
Yeah.
I
Well,
see.
and
Wait,
how protons are
this-
created when an electron and how neutrons are created when a proton and electron love each
All
other
right,
very
let's-
much.
Let's
And
move
then
on.
don't. And then
Let's
they
move on.
don't.
Okay, it says the radioactivity of sample one of iodine 131 was measured. The data collected are plotted on a graph below. Okay, determine the half-life of iodine 131 using the graph above. We've done one like this before. It started at 16,000 decays per minute, disintegrations per minute. So and this is measured with like a Geiger counter. So they're just holding a Geiger counter to the sample and it's clicking 16,000 times per minute. And then they want to know, when is half of that radiation or half of that radioactive isotope gone? So you're going to look down at 8,000. So I look here and here. Does that make sense that the half-life is 8 days?
Yeah.
Because you've gone from 16,000 clicks per minute, which is an activity, down to 8,000, which is half of that activity, and it took 8 days to do that. And you can confirm, so in another 8 days, what should it go from? 8,000 to
4,000?
4,000. 4,000, because it's half of it. And then in another 8 days, it should go from 4,000 to
2,000?
2,000. So you can you can confirm your half-life every 8 days. It's cutting in half, right?
So the half-life cuts each new number in half.
The time it takes 50% of the isotope to decay. Or if it's a chemical reaction, it wouldn't be isotope to decay. It would be the 50% of the concentration to deplete.
Okay, that makes sense.
Yeah, so you're just looking for the amount of time it takes to cut in half, and it should stay the same time frame every half-life. Like the half-life is constant; it's always 8 days.
Okay.
Okay. Okay, moving down to the next picture. It says the data can be used to show that the decay of 131 is first order reaction, and this has also constant half-life. That's another hint that it's first order, okay, as indicated in the graph below. So the question says, label the vertical axis of the graph above. What should be plotted here for a first order? So we can review this: 0th, first, and second. All these versus time.
Isn't it just K?
It would be the rate.
Yeah, so remember, so 0th, then usually just like the rate versus time is 0th, right?
Yeah.
This is linear. So this is our linearity check. Linearity check. So if rate versus time is linear, then it's 0th. Okay, but we want first order. So these ones you should you've got to memorize. So first order, what was the check? What did we do to the rate?
The natural
Natural
log
log.
of
Yep.
the rate.
Yep. So the natural log of the rate versus time is linear. So that's our answer. The natural log of the rate. And actually, to be specific, we shouldn't say rate. If you look back up here, they called it disintegration rate or decay. So it would be the natural log of the disintegration rate. Okay. And then for second order, do you guys remember?
Yeah,
It's
isn't it the
reciprocal rate.
yeah,
One
it's the
over.
inverse. 1 over.
Yep. No, yeah, not inverse, but reciprocal. The upside down rate, 1 over the
upside
rate.
down.
Yep. 1 over the rate versus time. If that's linear, then it's second order. So okay, so we've got the natural log. So commit those to memory. That'll save you some time. Okay, and they're actually not labeled on the equation sheet. I went and looked at the equation sheet. Let me scroll up. Here's what's given. They give you kinetics. This, it turns out, is first order, and this is second order, but they're not labeled. Okay, and we're actually going to use one of these in the next questions. Okay, and then this is the half-life. Again, they don't tell you what these are. You just need to be able to recognize them. They do tell you that one. My guess is they're probably going to give you a new equation sheet with the test, which I would be interested to see. That's got to happen in the next week or so. They've got to let you know what equation sheet to use, but they're going to take a lot off. Like the Henderson-Hasselbalch equation is probably gone. My guess, they might leave these, but these were in unit, I think these were in unit 8. So those will probably be gone. They'll probably leave all the equilibrium stuff. They'll probably leave all this stuff. Okay. So, but they might modify it. So just be prepared for a new sheet. Okay. So going back over, it says, what are the units of the rate constant? So we're on this one. What are the units of the rate constant K? So we know it's first order. So we can say rate equals K times the concentration of iodine 131 to the first, right? Oh, and they even tell us what the units are up here, I think. They call it decays per minute. So I could put this in decays per minute equals K times the, let's see, what do they want to call it? Decays to the first? Or I don't know what we want to say. Let's say, yeah, we'll call it decays in the first. Okay, so the question is, what does the unit have to be to make the, or what does the K have to be in to make the left side equal the right side?
1 over minute.
Yep.
Yeah.
Yep, that's correct. And for first order, you guys should, this would also, if you want to memorize it or you want to write down, first order is always going to be 1 over our time units. Okay, that's the units of K, units. Okay, it always works out that way for first. So if you're measuring something in molar per second, then the rate constant's going to have units of 1 over seconds. Yeah. So, yep, that's that one. Okay, explain how the half-life of 131 can be calculated using the slope of the line. So you've got this slope. Okay? And they just want an explanation. You won't be able to measure it because you don't have any scaling on the left. So, anybody have any ideas? Here, I'll jog your memory and go back to this guy. This, can you guys make it look like y equals mx plus b? Where this is the dependent variable, x is the independent variable, m is the slope, and b is the constant or the y-intercept. So if you look at this, the equation, first of all, time was what we graphed on our x-axis. So time is our independent variable, right?
Yeah.
So right here, in front of the time, that's kind of like the slope, right?
Yeah.
So
Mm.
time, that's our x, negative k, that's our m. And then if it bugs you that there's no constant over here, you can move this over to the other side. So I'm going to rewrite this underneath. I have the ln of concentration at time t equals negative kt plus the ln of the original concentration. So what that's saying, if you look at negative k, this only works for first order. If you look at the negative, or if you look at the slope is going to be equal to negative k. So your response to this question, and this is a confusing question, is you would just basically take the slope and change the sign. So make the sign positive, because it looks like you guys see on the graph, the slope is negative, right?
Yeah.
So you would take the value of the slope and turn it positive, and that would be equal to k. So slope equals negative k, so then k has to equal negative slope. Okay.
Weird. Okay.
It's, again, this might be something just to memorize to save yourself time. On the first order reactions, the slope is always equal to negative k. And for second order reactions, let's see if you can rearrange this one. I'll do it in, see if blue shows up. For second order reactions, I would have to move this guy to this side. I'd get something like 1 over A T equals KT plus 1 over A naught. So then what's the K value equal to in this one? The K value would equal the slope in this case. And then the y-intercept would be 1 over the original concentration. Okay. So something else to look at on the graph, and you guys, this one might be something where you just have to rewatch this video or watch some YouTube videos on kinetics, because this is kind of tricky stuff. They could have asked, how do you find the value of, maybe they labeled this point, oops, oh geez, what just happened? Maybe they labeled this point A, or we'll call it point A. How do you find point A? Well, then you would scroll back over, you'd find your first order equation, which is this one, and point A would be the y-intercept of our first order graph. So you would take the natural log of your original concentration. So again, using these equations is kind of tricky, and all they give you on the test is, let me erase all this stuff. They just give you these equations. So you have to be able to manipulate them. So, but yeah, this is just for linearized and linearized second order and first order. Okay, so they're there. You just have to know when to use them. Okay, next question. It says E, compare the value of the half-life of iodine 131 at 25 to its value at 50. And I got really confused when I saw this equation, or saw this question, because they don't give us any data for, like, they don't ever tell us up above if this was 25 or 50. So I thought it was going to have you like look at old graphs, but it just wants to know in general, what would you expect its half-life to do? 131 and 25. So generally, what happens to reactions as you heat things up?
They
Wouldn't that
They
the
speed up.
half-life
Reaction speeds up.
So
decrease?
what will happen to the half-life?
should
It'll
decrease.
increase.
Careful. Half-life is how long it takes. So if the reaction is going faster, then what's going to happen to the amount of time it takes to cut in half?
I have to go.
Yeah,
Be smaller.
it should be the time. So half-life is the duration of time it takes for something to decay. Oh geez, Linus is running around like crazy. So if things are reacting faster, then the time should be shorter. So the half-life, the half-life should be shorter, but I'm not exactly sure how this affects nuclear reactions. So I might do a quick Google.
Might just be weird. I think I have to go now.
All right, see you later. So let's do a quick Google since I'm here. Let me pull this up. Does temperature affect? Does what's going on? I can't type. Can somebody Google it for me? Does temperature affect half-life? I think that's all we need to search, and I could do it if my keyboard would stay up. Nope, it's not going to stay.
It says, although chemical changes were sped up or slowed down by changing factors such as temperature, concentration, etc., these factors have no effect on half-life.
Okay.
Each radioactive isotope will have its own unique half-life.
Yeah. There you go. So temperature shouldn't affect half-life because I think the forces are too strong. So I don't think they're going to ask a nuclear chemistry question. Should be shorter for, I would put something like this, for chemical reactions. But high temps may not impact nuclear reactions. So the default answer, had this been a chemical reaction involving, different compounds and not protons and neutrons, the answer would be increasing the temperature would cut the reaction rate, or it would make the reaction rate faster and the half-life would be shorter. But if it's half-life of something that's radioactive and it's nuclear reactions, I don't think nuclear reactions are affected by temperature as much. So I would be curious to see if, because I would bet that the AP, the guy doing AP questions on YouTube, I bet he'll be going through some of these. I would be curious to see what AP says on this.
Yeah.
So, but I would just be prepared. If it's a chemical reaction, reaction rate speeds up and half-life gets shorter. And if it's a nuclear reaction, no impact.
So, sorry, switching topics real quick. I logged onto my AP and see if can you guys see this at all? Is it blurry?
Share your screen with us. Oh wait, you're not on Google Meet. You're on Google Meet on your phone. Never mind. It's pretty blurry. Let me click on your picture just a second. Yeah, it's pretty darn blurry.
Okay, anyways, I'm on my AP, and then it says for the long questions for units 1 and 2, if I were to click on it, to see how many questions it has, it's only one question still.
Okay.
For the long units that are combined together. So I think all of them are just one question.
Okay, so how many units are there then?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 26.
There's 26 like free response questions?
Yeah, but they're like units 5 and 6, 4 and 7, like a whole bunch of different ones. But there's 26 total.
26 total, and then each question has like multiple parts, right?
Yeah.
Okay. Well, hey, we have, I don't know, we probably have about 10 to 12 more days worth of this. So if we just cover one of those a day, maybe two. So Keaton, since you're still here, why don't you try and log on to AP Classroom? Can you screenshot things and send them to me, like email them to me?
I can try.
Okay, or do what Savannah did and just take a picture of your screen with your phone and email it to me. However you want to do it. But let's do this for tomorrow. Can you guys each send me another question?
Yeah.
And then we'll have 2 ready. So Keaton, take your pick, send me one, and then Savannah, same thing, and I'll get it. I'll get it as long as you get it to me like by 10 a.m. tomorrow. I can do it.
So is it gonna be like the ones that are just posted on there, like the ones where like
yes. So you log into your classroom, you click on like the same little section, like had I assigned them?
Assignment list.
Okay.
Yeah, go to assignment list, and then you should see them. What are they called?
So you go to view assignment list, and then there says assignments, and then on the other side says optional practice. Click on optional practice. It has a little green button by it, and then it'll show all 26, or there's technically 28 because I did 3 already.
Gotcha.
But it'll show all 28, and then you click on which one you want to do.
Okay,
then
and those are all current. And does it just cover like all the units?
I think it covers all the units that they could be testing on.
Yeah, it only
Okay.
goes to Unit 7.
Yeah, there you go. So, yep. Oh, okay. So I will see you guys. I'll see you guys. Oh, and you have till Wednesday. You don't have to send it to me. So if you send it to me by Wednesday, we're good to go.
All right, cool.
Okay.
And yeah, we'll just try and do as much as we can.
All right.
Okay, awesome. Thank you.
All right. See you
Yeah.
guys later.
See ya.
Bye.
Bye.